Hello students, in this video we will study about spectral series. In the chapter atoms, we already studied about different atom models, J.J. Thomson atom model, then Rutherford's atom model, then Bohr's atom model. In Bohr's atom model, the extension of it, in Bohr's postulate, when we talk about, we are going to talk about the electron jumping from one orbit to other orbit gives out energy. It gives out energy in terms of h nu, that is E is equal to h nu. This is called Einstein's frequency condition. Okay, difference in the level. Now, when we studied about it, we learned that energy is equal to minus 13.6 upon n square electron volt. This was the derivation we did for the energy in the nth orbit. Now, what we are going to discuss is, suppose if I have got with me the, let us say, positive nucleus, let us say this is the first orbit, second orbit, third orbit, and then fourth orbit. I can have more orbits which I am not going to consider now. Suppose if I say n is equal to 1 and n is equal to second, n is equal to 3, n is equal to 4 and n is equal to 5. The electron can jump from a higher orbit to a lower orbit. Now let us say, when it jumps from a higher orbit, that means from 2 to 1, what will happen? It will give out energy. This energy is in terms of h nu. So h nu is nothing but hc upon lambda. We can express in terms of wavelength. Now, we can derive a relationship for all this. You have to remember, spectral series and spectral lines were studied in 1850s itself, before the invention of discovery of electrons, protons or anything by J.J. Thomson. So, from the sun, when light is coming, and that light has been studied with the help of a spectrometer. The spectrometer, when we study the lines are there, different lines are there. For example, when you take, for example, the solar spectrum, it will have 4 prominent lines. They are called H alpha, H beta, H gamma and H delta. So this helps you to identify the element in the particular star or anything you say. So how can we derive an equation for this? It is going to jump. Now the electron can jump from second to first orbit. Remember one thing, electron is in the orbit means when it possesses a particular amount of energy and it will stay in that particular orbit. Is imaginary. Just like in our solar system, earth is revolving around. There is no path. Yes, there is no path being drawn. It just goes in that particular path. That's the imaginary one. So here also, electron can stay in with a higher energy and it is going to fall back to the first orbit. It can be in the fourth level, it can fall into the first level. So these things, it is called Lyman Series. Okay, these are all named after different scientists and this is referred to as Lyman Series. That means electron jump into the first orbit from any other higher orbit. Right, now 2 and 3 also we will study in the similar way. Now before going to that, let us first derive a relationship for the wavelength. We need to derive a relationship for the wavelength that will assist us to understand better. Okay. Yes, let me say, if I have one energy level, this is the ground energy level, n is equal to 1. This is the ground energy level. Okay, so let me draw a little bit more clearly. Yeah, let me take, this is the ground energy level, n is equal to 1, and I take next level, n is equal to 2. Then let me take the next energy level, n is equal to 3. The next, n is equal to 4. The next, n is equal to 5. I can go on drawing like that till n is equal to infinity, very far away. I can take a thing which is very far away. Okay. Now, what is the formula? We have to derive an equation for all these things. We know that energy in the first level is equal to minus 13.6 upon, let us say level is n1 square. Let us say energy in the second level, it is minus 13.6 upon n2 square. Now from n2 to n1, so we have E2 minus E1, which is equal to minus 13.6 upon n2 square minus of minus, that is plus 13.6 upon n1 square. So I can write this as 13.6, I take it out here, of 1 upon n1 square minus 1 upon n2 square. So this is the change in energy. This change in energy should be expressed in terms of wavelength. We know h nu is equal to the energy which we are having, that is 13.6 of 1 upon n1 square minus 1 upon n2 square. Okay, so this is what the formula is. I will say here, instead of this, hc upon lambda, okay, that is equal to 13.6 of 1 upon n1 square minus 1 upon n2 square. Yes, I got this now. This c, velocity of light, h, Planck's constant, I remove these two, then I get 1 upon lambda, and I will get a value here, h and c will come here. Okay, so all these are going to be now meter. When I find out the value of this whole thing, it will give you a constant, and that is called Rydberg's constant. It is referred to as Rydberg's constant, R of 1 upon n1 square minus 1 upon n2 square. Yes, 1 upon wavelength is also called wave number, but we don't use this so often. We talk about only wavelength. So this is the formula, and where the Rydberg's constant is 1.1 into 10 power 7 per meter, 1 upon lambda, so it is per meter. Now let us study about the different spectral lines. Yes, n1, I am going to take n1 is equal to 1 and n2 is equal to 2, 3, 4 higher values. So from second, the electron jumps to the first, 3 to 1, 4 to 1, 5 to 1. This, when it jumps to the first level, this is called Lyman series. Okay? And second, it can come and jump into the second level. So when n2 is equal to 2, from higher level it has to jump. So n1 is equal to 2, n2 will be 3, 4, 5 and so on. Right, that is the second level here. So I have just a thing it here, 3 to 2, 4 to 2, 5 to 2, 6 to 2. Yes, and this is called Balmer series. This is referred to as Balmer series. Right, this Balmer series is very important. Why? Because Balmer series lies in visible spectrum. It lies in visible spectrum. When this is in visible spectrum, what is before that is ultraviolet spectrum. Ultraviolet you cannot see. Now visible, right? Suppose if n1 is equal to 3, then what will happen? n2 will be 4, 5 and 6 and so on so forth. Right, now I come to the third level, okay, and from 4 to 3, 5 to 3, 6 to 3, 7 to 3, like that. And Lyman, Balmer, and then you have passion. Okay, this is Okay, this is called Passion series. Now, Passion series falls in infrared region, right? Lyman series, Balmer series, Passion series. Then you have bracket series, then fund series. They are not so important because they are going to fall in the 4th level. Then it's called bracket, and it fall in 5th level. Then it's called fund. It can happen, but we are concerned more with these 3 particular parts. Why? Because what is happening here in the Balmer series, that is invisible, which we can see. The spectrum which we get from the sun is observable, and we are able to see that, and that is why this is very important. Again, little less than that, that is ultraviolet radiation. Yes, that is Lyman series, and little more than that, that is infrared. So in electromagnetic spectrum, a narrow window, visible and ultraviolet and infrared. This is the useful, the basics of it. Now, in this video, we have studied about the spectral series, different names of it, and I told you the formula: 1 upon wavelength, and R is Rydberg's constant, and N1 is the level, it is going to first level to jump, N2 is the next level with which we can do lot of numericals. With this, we have completed the unit called atoms, right? And the next unit is nuclei, right? And thank you so much.